So, as you recall from earlier discussion, we talked about when forces are not balanced, we get acceleration. So Newton's second law tells us that when forces are not balanced, objects accelerate, and that acceleration depends on two things. Number one, net force is proportional to acceleration, and we looked at this with the fan carts, and we're going to postpone the analysis of that data, which is going to put things a little out of sequence, but this should just make that make more sense when we look at that on Monday. So we could say that acceleration is proportional to net force, and then we also know that if we apply a constant force and we vary the mass of an object, that the acceleration would be proportional to 1 over mass. In other words, acceleration is inversely proportional to the mass. So Newton's second law says if we take those two relationships and put them together in one single equation, we get Newton's second law, which says that the net force applied to an object is equal to mass times acceleration. We started this unit with looking at situations in which the acceleration is 0. So really, we kind of put that in reverse order, because if the net force is equal to 0, then that dictates that the acceleration is equal to 0. So if acceleration is 0, net force has to be equal to 0. If acceleration is not 0, then there must be some unbalanced force. So today in class or tomorrow, depending on when you see this, you're going to be starting to work through some problems in which the forces are not balanced. In AP, just like with equilibrium, we deal with both the x and the y direction. So if Newton's second law says that the sum of all forces must equal mass times acceleration, that means the sum of all forces in the x direction are only going to produce acceleration in the x direction. The sum of all forces in the y direction will produce acceleration in the y direction. So it'll be very likely in a problem where the forces in the x direction may not be balanced, causing, a cart to accelerate. For example, the fan carts. The fan carts were accelerating in the x direction along the tabletop, but they were not accelerating vertically up towards the ceiling or down towards the floor, because the forces in the y direction were balanced. So I thought I would take you through a couple of problems which should guide you through two things: the WebAssign and the practice problems that you'll be working on in class. So as soon as you are able to work through those practice problems that were given to you, you can use the rest of the time for the WebAssign. But let's look at a couple of examples. You're going to find that we're not going to approach these any different, except the fact that they're not going to add up to 0 anymore. They're going to have a sum, and that sum must be equal to mass times acceleration. So in the first one, a 50-kilo box is pulled along a rough ground, and you want to start to look for important terms. So a rough ground implies that there must be friction, and we're going to spend some time on friction next week, but for now we know that there has to be friction, and then the physics in the problem tells me that there has to be friction too. It's pulled by a rope that has a tension of 130 newtons, and we see that the box will accelerate at 2 meters per second squared as a result. We want to determine this force of friction between the ground and the box. So let's start out with number one. We do these the same way every single time. Let's do a free body diagram for this. Get this out of the way. So it says that we are pulling with on a rope, and the force in that rope is 130 newtons. Let's save the numbers for later. And we also see that there is a rough ground, so there's some force of friction acting in the opposite direction. Friction always opposes motion, and as a result of this, the box is going to accelerate to the right. Okay, so there is our free body diagram. So there are also two other forces acting on this as well. We have the weight of the box, and we have the force of the table or the ground pushing up the normal force. that, and we don't have to dwell on it, but that's a good example of some of the forces in the y direction are going to equal 0 because the acceleration in the y direction is 0. So the normal force minus mg equals 0. So my normal force would have to be equivalent to mg in this case because there are no additional vertical forces. Now this, even though there's no acceleration in the y direction, is going to become important very soon because normal force is an important piece of friction. So when we explore friction a little bit closer, the normal force from the y direction will become part of friction in the x direction. So if we go over to the other side, we can say that the sum of the forces in the x direction must equal mass times acceleration. And again, please be aware that when I say the sum of the forces in the y direction are equal to 0, I am still saying that the sum of the forces in the y direction are equal to ma in the y direction. It's just that there is no acceleration in the y direction, so it equals 0. So we're not really creating a new rule, we're just expanding a little bit. So let's write this out. So my equation says that T to the right minus the friction force to the left has to equal the mass times the acceleration. So now let's read. It says a 50 kilogram box is pulled along the ground. There's 130 newtons of tension in my rope, and the acceleration is 2. What is the force of friction? So I can rearrange this. I'm going to put friction on the other side to make it positive. So the friction force has to equal the tension minus ma, which means I have 130 newtons minus mass is 50 times 2 minus 100 newtons means that my friction force has to be equal to 30 newtons. And if I want to put the direction in there, negative 30 because it's going to the left. So let's think about what this means. If a 50 kilogram box is accelerating at 2 meters per second squared, then let's start with the right side of this equation. The mass times the acceleration is 100 newtons. Positive. If the box is accelerating to the right, then I have to have a net force of 100 newtons to the right. So what that tells me is no matter how many forces are acting on the box, I need 100 more newtons of force to the right than I do to the left. So if I started out with 130 newtons of tension in the rope, then friction must be equal to 30 because I need 100 newtons of net force acting on the box. Let's take the same box and hang it from a rope now. So if my box hangs from a rope and the maximum tension that this rope can sustain is 700 newtons, what is the maximum acceleration that I can lift this with? Okay, so let's again draw my free body diagram. This time I have tension in the rope acting up. Let's draw it from the center of mass. And I have the weight of that box pulling down. And it tells me that I want to figure out, so in other words, if I pull up hard on that rope and if I exert an upward force in T greater than the weight of the box, then there will be a net force up and the box will accelerate up. The maximum force that I can apply to T before it's going to snap on me is only 700 newtons, so that means there's a limit to the acceleration that I can give this box. So once again, we just said this is only a y problem. I have no x forces. So the sum of the forces in the y direction have to equal the mass times the acceleration in the y direction. So that means T minus mg has to equal ma. And we're going to go ahead and put in T max. So when I solve it using T max, that's going to mean that the acceleration I get is the maximum acceleration. So let's solve it out. T minus mg, so I have T max is 700 newtons. The weight of the block, it's the same 50 kilogram block, so that's 500 newtons of weight. Has to equal 50 kilograms of mass times this maximum acceleration. So if I work this out, I get 200 newtons over here, which is my net force, 200 newtons of net force acting on a 50 kilogram mass means that I can only accelerate at a maximum 4 meters per second squared. Okay, let's do one more. Let's take the same 50 kilogram box and let's make this situation a little more complicated. So now we're going to put the box on a table, and let's keep the table frictionless for now. Let's connect a string to it, and now let's use a hanging mass to accelerate that box along the table. So we have a 50 kilogram box, we have a 10 kilogram mass hanging, we have no friction, and we want to figure out two things. What's the acceleration of the box, and how much tension is in that string? So this looks a little bit like an equilibrium problem, but it's not, because the box is moving. So this is a situation where we have two objects, so I need two diagrams. Just like with equilibrium, two objects mean two diagrams. So let's go ahead and diagram, then we're going to talk about something we're going to do a little different with direction when we have problems that involve pulleys. The 50 Newton or 50 kilogram box has a force of tension to the right. Now, we also have normal force and weight acting on this box, but we're going to go ahead and ignore that. The box has no acceleration in the y direction, so we don't need to, and there's no friction. Like I said, normal force affects friction. So let's just focus on the x. Now when I go over to the other one, though, I notice that I have mg, and we better number these because both of these masses, so let's call that m1g acting down, and then we have the same tension acting up. Remember, one rope, one tension. The pulley here does nothing but redirect it. So this is what we need to do with direction. So pay attention to this part, because this is where the wrong sign will lead to the wrong answer. This system has one acceleration. When this box moves to the right, this mass goes down. So we want to say that that's the same direction. So we're going to say that this is the positive direction. So over here on my hanging mass, that means down is the positive direction, and over here that means to the right is the positive direction. That's extremely important because we want to relate them with the same acceleration, because we normally call the right a positive x acceleration and down a negative y acceleration, but since both of these boxes or objects are connected, we want to say that they both have the same acceleration, so we have to kind of unify the directions. So that means on the 50 kilogram box, we can write our equation. T is the net force. There's nothing, and let me be consistent here. Sum of the forces equal mass times acceleration. This is the mass or the acceleration of block 2, so we're just looking at the 50 kilogram. So that means tension must equal m2a. Okay? Now if I go over here to the other side, now this is where you have to be careful. Sum of the forces now on block 1 has to equal m1a. Same a, so I don't have to put a1 and a2. But we've defined now the weight, which is pulling down, to be the direction of the acceleration, which is positive, minus t equals m1a. Okay, so we have a system of equations, but it's a relatively easy system of equations. My left equation has both unknowns, t and a. My right equation has two unknowns, t and a. So why not solve for tension over here? M2 is 50, so 50 kilograms times a. And now we can just substitute that in over here, and that gives us m1, which is 100 newtons, m1g, minus 50a equals m1 is 10, 10a. So we can now calculate the acceleration. So 100 newtons has to equal 60 A. So the acceleration has to be 100 newtons over 60 kilograms, which gives me whatever, 1.7-ish meters per second squared. So hopefully these three examples, again, we did the same thing every time. Diagram it out, write the equation. The sum of the forces must equal the mass times the acceleration. If there is no acceleration, the sum of the forces have to balance out. Same thing with a vertical situation, the up force minus the down force has to equal mass times acceleration. We were able to find that maximum acceleration. Third situation, a little more complicated with two objects. Two objects means two diagrams. We diagrammed them out, wrote an equation for each one, knowing that they had two things in common. They were both connected by the same string, so same T, and they both moved as one system, same A. That gives us a nice convenient little system of two equations to solve for two unknown variables.